Hello learners, you are listening to our learning series. In the previous session, we have gone through the basics of quality and GD&T for a manufacturing industry. In this session, we are into the basics of 7 QC tools. Every quality professional must know this. Quality problems always need a data and analysis to get resolved. This 7 QC tools is a foundation of problem solving in manufacturing and service industries. This session will be helpful for a fresher who is starting their career as a quality professional. Let's begin today's session. 7 QC tools. The 7 QC tools are a set of graphical and statistical techniques used to analyze a process, identify root cause and drive continuous improvement. Originally popularized by Ishikawa. Where it will be useful? It will be useful in any data-driven decision-making environment. As the name insists, there are 7 quality control tools. They are check sheet, cause and effect diagram, Pareto chart, histogram, scatter diagram, control chart and stratification. First, let's see what check sheet is. It is the structured way to collect the data. The data has to be collected at the location where the data is generated. It is always the first input to our analysis. The check sheet is sometimes called as tally chart. This is an example of a check sheet. This check sheet has many data, complaint wise, day wise also. The complaint wise total is there and day wise total is also there. And if applicable, you can also collect shift wise data. We must collect data in various factors as much as possible so that it will be helpful for our analysis better. Next is cause and effect diagram. It is also known as Fishbone diagram or Ishikawa diagram. This is one where one person cannot work. It is a brainstorming session. We should collect data from various level of peoples who are all involved in that particular process. The causes may be silly, but we should consider that as a probable cause in this session. After collecting all the probable causes, we should categorize each cause from different people in 6M form in a template. That is man, machine, material, method, mother nature, that is environment and measurement. This is an example of cause and effect diagram. Imagine that there is a problem in an airport which is customer is waiting for a long time. Problem comes here. They called for a meeting with all relevant people there. They collected data in the 6M form, that is man, method, material, machine, mother nature and measurement. The probable causes also listed here like too many training agents and loud office background noise make it difficult for the agent to concentrate, missing customer history data in the primary database, no real-time dashboard to alert supervisors when the queue is backing up. Likewise, you can add up probable causes as many as possible. From this data, we have to finalize the possible cause by using YY analysis. So next is Pareto chart. It is a combination of bar chart and line chart. Also, it gives the cumulative total percentage. The Pareto principle is 80-20 rule. What is 80-20 rule? The problem solving team has to focus on vital few problems than trivial many problems. Means attacking 20% of the defect will reduce the 80% of the loss. To create a Pareto chart, we need to understand its 3 main parts, that is axis, it has axis and bar chart and line chart. The x-axis shows the problems or complaints. You see there are 2 y-axis. One is in the right and one is in the left. The left y-axis measures the frequency of occurrence, that is cost or time, etc. And the right y-axis measures the cumulative percentage of the total ranging from 0 to 100. And there is a bar graph here. Each bar graph represents the category, that is type of customer complaint or product defect. They are always arranged from tallest to smallest. This is very important here. Next is line graph. It is the cumulative percentage line. It shows the running total of the bars as you move from left to right. Finally, it has to end up in 100%. So next is histogram. It is completely a bar chart that has been specialized for frequency distribution. It is a snapshot of your process personality, showing you not just how much data you have but how that data is behaving. There are many shapes that project you the behavior of the project. First is bell-shaped graph. It is a normal distribution. That means the process is stable. Next is skewed left or right. That means the process is pulled in one direction due to some error in a process. Next is bimodal graph. That is double peak. It shows that you are dealing with 2 processes or 2 shifts or 2 different operators. Next is comb chart, that is zigzag or tall and short. It shows the error in a measurement due to rounding off the values in data collections and so on. Now, how to draw a histogram? First, collect the data. Gather at least 50 to 100 points for a clear picture. For example, let's say you are measuring the weight of coffee bags coming out from a production line. Now you have 100 set of data. From that, find the maximum value and the minimum value. To calculate the range, the formula is R is equal to maximum minus minimum. Now we got the range. Next, determine the number of bins, that is K. Each bin represents a specific range of value, that is, the data has to be divided into small groups. For example, if you have 100 set of data, 10 to 20 is one group, 20 to 30 is one group, and so on. The common shortcut is the square root rule. K is equal to square root of n, where n is the total number of data points. We have 100 data, so n is equal to 100. So K is equal to root of 100 is 10 bins. Now we have 10 bins. Then calculate the bin width. Divide the range by the number of bins to see how wide each bar should be. H is equal to R by K. We have R range and we have K, so H is equal to R by K. Now we have to create the frequency table. List your bin intervals and count how many data points fall into each. The bin intervals is in this side and frequency is there in this side. Finally, we have to draw the histogram. First, draw the axis. First interval on the horizontal plane, that is x-axis, weight. Here the data are divided into equal intervals called bins. Then frequency on the vertical y-axis. Here we can see how many times the value falls with that specific bin. Next, draw the bars based on the data collected. The height of each bar corresponds to frequency. The crucial part in a histogram is the bars must touch because the data are continuous. In this chart, the lower specification limit is 490 grams and upper specification limit is 510 grams. The distribution is roughly a bell shaped, showing a stable and predictable process. You can see many of the values are near to 500. See, 3 bars are high. So this is how, based on the shape of the graph, we have to check whether the process is stable or not. Next is scatter diagram. While a histogram shows you the personality of a single variable, a scatter diagram is used to see the relationship between two different variables. In quality control, this is the detective tool. It helps you to prove or disprove if a change in one factor like machine temperature causes a change in another factor like product defect. Let's see how to create a scatter diagram. First, we need to collect a paired data. You need a data point that happens at the same time. For example, imagine we want to see if there is a relationship between number of hours a student spent on studying and the scores they achieved in an exam. We have collected data from 10 students. Next, we need to draw the axis and plot the points. Plot the causes of the problem, that is number of hours spent in x-axis, and effect of the problem, that is exam score, on the y-axis. For every pair of data xy, place a dot. If the dot seems to follow a line, then draw a line which is called as line of best fit through them. This line is called as regression line. Next, the most important part of scatter diagram is the pattern the dots form. This pattern tells you the strength and direction of the relationship. There are different patterns like slope up right. It is a positive correlation. As x increases, y also increases. Next is slope down right. It is a negative correlation. As x increases, y decreases. Next is cloud. There is no correlation at all. There is no apparent relationship between the two. Changing x won't help you control y. Next is tight cluster. It is a strong correlation. The variables are very closely linked. X is a reliable predictor of y. Next is control chart. Control charts are used to monitor whether a process is stable and performing consistently over time. It helps us to distinguish between normal variation and abnormal variation. It is used to monitor the process performance inline during the running of production and detects unusual variations early. As it detects a variation early, it reduces the defects automatically. That's how it improves process stability. There are many control charts based on the data. For variable data, that is numerical measurement value, we can use X bar R chart and X bar S chart. For attribute data, that is S or no values, we can use P chart, NP chart, C chart and U chart. Let's see how the control chart looks. It has three important lines. One is upper control limit, one is lower control limit, and one more is center line. These are control limits, and please note that these are not the specification limit. Specification limit is different and control limit is different. Specification limit comes outside the control limit. After plotting the data, we need to calculate the CP and CPK. CP is process capability and CPK is process capability index. Now we are going to draw a control chart and calculate CP and CPK. For that we need to calculate X bar and X double bar. Now we have n number of data. So X bar is X1 plus X2 and so on to Xn divided by n. So you got a X bar. X double bar is average of all X bars. Next calculate R and R bar. R, as you know, we have calculated in histogram the same. Range is equal to maximum of your data collection and minimum of your data collection at a particular point. R bar is average of all R's. Next, finding the UCL and LCL, upper control limit and lower control limit for both the charts for plotting. For X bar chart, we have already X double bar and R bar which we have calculated in the previous slide. And so UCL is equal to X double bar plus A2 R bar, LCL is equal to X double bar minus A2 R bar. For R chart, UCL is equal to D4 into R bar and LCL is equal to D3 into R bar. Now only thing we don't know is A2, D3 and D4. What is that? It is the constants. There is a constant table for the control chart. We have to take the A2, D3, D2, D4, all these things from the table. Now calculate the CP and CPK for process capability check. CP is equal to USL minus LSL by 6 sigma. Sigma is equal to R by D2. We know R, we know D2, everything. If you see, this is USL minus LSL. This is not UCL, LCL. This is upper specification limit and lower specification limit. This is the formula to calculate the CP. Now CPK is equal to minimum of USL minus X double bar by 3 sigma, X double bar minus LSL by 3 sigma. So this is how we have to calculate the CP and CPK. The acceptable limit of CP and CPK is CPK should be always greater than or equal to 1.33 and CP should be always greater than CPK. If the CPK is less than 1.33, then we should understand that the process is not stable and have some errors. So we have to address it immediately. This is an example of X bar and R chart. Here you can see X bar chart on the top and R chart on the bottom. There are some instruction in a control chart which tells that we need to take action immediately. They are one or more points falling out of control, 7 consecutive points in increasing trend or decreasing trend, a run of 8 consecutive points on one side of control limit, a cyclic pattern, that is 14 consecutive points in an up and down manner, 2 to 3 consecutive points near the control limit, and 4 or 5 consecutive points in a row in one side, and if there is a mixture pattern. When we see such pattern, we need to stop the process and take action immediately. Next is stratification. Stratification means separating data into groups or layers. So you can see patterns that are hidden when everything is mixed together. In simple words, it is sorting information to understand the real cause of the problem. For example, suppose a factory finds many defective products. Total defect is equal to 120, but after stratification by machine 1 has 15 defects, machine 2 has 20 defects, machine 3 has 85 defects. Now it is clear that machine 3 is a main problem. Without stratification, we only know the defects are high, 120. Let's see how to stratify the data. First, identify the factor, example machine or operator or system, etc. Then collect the data with respect to the factor. Then organize it and using the graph. Either you can use a histogram or Pareto to visualize the difference. Finally, we need to investigate the specific problem which gives the higher defects. This is how stratification works. As of now, we have gone through the basics of 7 QC tools. Hope it will be helpful in your day-to-day problem solving and gives continuous improvement. Please do visit this channel for continuous learning. Thank you.